Hey everyone, welcome back to another video by Camroom 5. In the last video, we were talking about alkenes. We said that alkenes have carbon-carbon double bond, which is apparently stronger because it's a two bond between the same carbon atoms, but the pi bond between these double bonds is weaker. So the pi bond can break down easily. We talked about the idea that pi bond is actually electron density spreaded above and below the internuclear axis. And that is why these electrons from the pi bond can be donated to an electrophile. Electrophile is any chemical species that can accept electron pair. We talked about the electrophilic addition mechanism, which begins with a hydrolytic bond fission between two atoms. When an atom loses electron pair like hydrogen, it becomes electrophile. Then carbon donates the pi bond to this electrophile. Between the two carbon atoms, there can be two possibilities. If the carbon on the left makes a bond with the electrophile, then the carbon on the right, becomes positively charged. If the opposite happens, then the carbon on the left becomes positively charged. This does not make sense in a symmetrical molecule, but right now we're going to be talking about asymmetrical molecules. So let's begin the example of electrophilic addition on asymmetrical alkenes. Let's begin our example with an alkene which has two methyl groups on one of the carbons and two hydrogens on the other carbon. Let's highlight them with yellow and red. We know this compound is named carbon 1, 2, 3, and this would be a branch. So when you name it, it becomes 2-methyl prop-1-ene. This is the IUPAC name of this compound. Let's begin our example with using hydrogen bromide like last time. Hydrogen bromide has hydrogen with a partially positive atom and bromine is the partially negative atom. Don't forget to put the partial charges. The hydrolytic bond fission happens when an arrow moves from the center of the bond towards the bromine atom. This makes hydrogen as an electrophile. The next arrow you should be drawing is from the center of the carbon-carbon double bond towards the hydrogen. Now, the most important thing is there are two possibilities. Let's draw the rest of the structure exactly the same way. The carbon on the left with two methyls and the carbon on the right with two hydrogens. The pi bond is gone, so I'm not drawing it. Again, the carbon on the left has two methyls and the carbon on the right has two hydrogens. Let's highlight them with the same colors. Yellow one is the left one, red one is the right one. There are two possibilities here. If the carbon on the left, which is carbon number 2, if the carbon on the left, carbon number 2, and then right one, the red one is carbon 1. If the carbon number 2 makes a bond with the electrophile by using the pi bond, then you draw it like this. Carbon 2 makes a bond with the electrophile hydrogen, and carbon 1, the carbon red one, becomes a positively charged because its electron has been lost. The pi bond was an electron between these two, right? But now the yellow carbon ditched the red carbon and made a bond with the electrophile using the red carbon's electron. The electron pair was shared between yellow and red. But now the yellow one is making a bond with the hydrogen using the electron of the red carbon. So carbon 1, the red carbon, has lost its electron and now it has none. So it becomes a positively charged carbon. We call it a carbocation. So let's label it carbon 1 carbocation Or another possibility is that the electrophile makes a bond with the red carbon. Electrophile makes a bond with the red carbon using the pi bond electrons, while the yellow carbon has lost its electron. Because if you remember, the yellow carbon and the red carbon had two electron pairs, right? One was the sigma and one was the pi. If yellow carbon uses the pi electron to make a bond with hydrogen, then it's injustice with red. Or another possibility is that if the red carbon makes a bond with the hydrogen using these electrons, then it's injustice with the yellow. So it's very important to notice that whichever carbon makes a bond with hydrogen or electrophile, the other one becomes carbocation. Like on the right side you can see carbon 2 becomes carbocation. Now you should ask yourself, let's put the positive on carbon 2. Yeah. Now you should ask yourself, which one is more stable? Now here we should consider the side chains. Carbon number 2 has two methyls and carbon number 1 has no methyls, only small hydrogens. The methyl groups or alkyl groups have their own hydrogens, have their own bonds. So at least they can share some electron density towards the carbocation. Let's explore this idea a little more. When positive charge is on carbon number 1, the carbon number 1 wants to ask for some electrons from the nearby hydrogens. Nearby hydrogens have no electrons of their own. Hydrogens have no electrons. Hydrogens are not good electron donors because they don't have any electron of their own. So they can't share any electron density with the carbon. The carbocation will not be stable because it will not be able to receive any help, any electron, any support from the nearby hydrogens because hydrogens have nothing of their own. That is why this is not stable. But when you notice on the right side, when the carbon 2 gets a positively charged to make a carbocation, there are two methyl groups. These methyl groups have their own hydrogens and one carbon atom each. So they can at least share some electron density towards the carbon. This support is known as inductive effect. So this electron donor effect, electron sharing effect, this support which the methyls are giving to the carbocation to make it stable is called inductive effect. So this is positive inductive effect. So let's say that methyl or alkyl groups means any carbon chain, right? So methyl or alkyl groups provide more positive inductive effect. Positive inductive effect. Now what is positive inductive effect? It means the capacity to share electron density towards carbocation. So out of the two possibilities, the one on the left with carbon 1 carbocation is less stable, intermediate. It's a less stable intermediate, which means it's formed in the middle. It could be formed in the middle as a step in the reaction, but it's not pretty stable. But the one on the right is more stable intermediate. So at the end, we know that when the pi bond is donated to the electrophile, you can have two intermediate possibles for an asymmetrical alkene. either a less stable intermediate with less positive inductive effect or more stable intermediate with more positive inductive effect. Let's not forget to write this. Less alkyl groups, so less positive less positive inductive effect. While on the right side you can see on carbon 2 carbocation more alkyl groups, so more positive inductive effect. Let's move forward, reminding us of the both intermediates. One had less positive intermediate, the other had more stable, perhaps better intermediate. We know we were highlighting it with yellow and the red carbon. So red carbon getting a positive charge or yellow carbon getting a positive charge. We know the one with red carbon positive charge, carbocation, is less stable. The one with yellow carbon getting a positive charge is more stable. We know that look like this. Now, the second step is also two possibilities because there are two different carbocations, two different intermediates. The bromide, which is a nucleophile, could attack whichever intermediate is there. So it will donate the lone pair to the carbocation. Make sure to donate the lone pair. Lone pair is donated from the nucleophile. Very important point. So first product could be both carbons, the methyls on the carbon of the left, hydrogens here, this was a hydrogen here, and there was a bromine attached on this carbon. This becomes your longest chain now. This becomes your longest chain. This becomes a methyl branch. So you will call it carbon 1, 2, 3. So you will call it 2 methyl. Bromo comes first apparently. So 1 bromo, 2 methyl propane. The second possibility would be that the carbons are here, the methyls, the hydrogens here. This is your hydrogen, which was the electrophilic hydrogen, which came in through the reaction, and the bromine. This becomes still your longest chain. Again, the methyl is here. When you number it in a way, carbon 1, 2, 3. So it would be named as 2 bromo, 2 methyl propane. So there are two possible products, one from the less stable intermediate on the left and one from the more stable intermediate on the right. The less stable intermediate gives you minor product and the more stable intermediate gives you major product. Now, we should know a rule to remember things which is known as Markovnikov rule. A Markovnikov rule will help us realize how to predict the products. So Markovnikov rule is not exactly asked in the paper, but we should know how it's applied. The Markovnikov rule says that when electrophilic addition is going on, the electrophile is attached on the less branched carbon. So it's related to asymmetrical alkenes, by the way. So in electrophilic addition of alkenes, the electrophile the electrophile is bonded to the carbon atom with less alkyl groups. And when you say less alkyl groups, it could be more hydrogens. More hydrogens. So I know the concept today was very tricky. We'll really quickly revise this concept here. We started with asymmetrical alkene, which looked like this. Then we made the heterolytic bond fission between HBr using the partial positive and partial negative charges. The carbon donated the electron pair to the hydrogen. That was step number 1. We get two carbocations in this scenario. Either the one with methyls becomes positively charged and hydrogen attached to the carbon with more hydrogens, which is the yellow carbon, carbon number 1, or the hydrogen is attached to the carbon with more hydrogens, the carbon on the right, which I'm highlighting with a red pen. Let's do the red and yellow thing again. And the yellow carbon becomes positive because hydrogen is attached to carbon 2. These are the two possibilities. Then we said one of them is more stable intermediate, the other is less stable intermediate. Then we said bromide nucleophile can attack in both scenarios. We make an arrow from the lone pair, so either like this or that. Both can give you like their own product. The bromo could be attached on the second carbon with the hydrogen on first, or the bromo could be attached on first carbon. Here we have a concept of major and minor product. More stable gives you major product, less stable carbocation gives you minor product. I hope this idea is clear to us. Stay tuned, guys. Thanks.